Imagine a World War II Atlantic, where ships and aircraft move without a reliable way to know their exact position. Navigation depends on stars, dead reckoning, and manual calculations that fail at night or in bad weather. Convoys drift off course. Bombers miss targets. Coordination breaks down over long distances. This was the reality before radio navigation systems became operational at scale. During the war, one system turned radio signals into precise coordinates, allowing forces to navigate without visibility. One of the engineers who made that system operational was Ivan A. Getting. Ivan Alexander Getting was born on January 18, 1912, in New York City, United States. He grew up in an urban environment during a period marked by rapid industrial and technological development. Unlike many rural-born engineers of the early 20th century, Getting was raised in close proximity to academic institutions, infrastructure, and emerging scientific culture. His family background was not centered on military service or weapons development. There is no indication that his parents were engineers or scientists involved in advanced technical fields. His early education followed the standard American school system. From an early age, he showed aptitude in mathematics and physical sciences, subjects that would later define his professional trajectory. Getting pursued higher education in physics and engineering, focusing on applied science rather than purely theoretical research. His academic training emphasized the behavior of physical systems, signal propagation, and measurement. He was educated to analyze problems where timing, accuracy, and system reliability were critical. This background prepared him for work involving large-scale technical systems rather than isolated devices. After completing his studies, Getting entered professional research environments that dealt with radio technology and applied physics. His early work placed him in contact with problems related to signal timing, synchronization, and interpretation. These issues were already emerging as critical limitations in navigation and communication systems before the outbreak of World War II. At the beginning of his career, Getting did not work on navigation systems directly. His role focused on understanding how radio signals behave over distance and how timing inaccuracies affect system performance. This work would later become central to his wartime contributions, even though it was not initially pursued for military applications. As World War II approached, the limitations of existing navigation methods became increasingly evident to military planners. Long-range aircraft and naval convoys required position estimates that could not depend on visual reference, celestial navigation, or manual calculation alone. These constraints created demand for engineers capable of translating radio theory into operational systems. Getting's background in radio physics and timing accuracy positioned him for this type of work. During the early years of the war, Getting became involved in research environments focused on applied military problems. He worked within teams addressing navigation and coordination challenges using radio signals. His responsibilities were not centered on hardware construction. Instead, he focused on system behavior, signal timing, and the interpretation of radio measurements under real operating conditions. Getting was associated with the MIT Radiation Laboratory, an institution created to accelerate the development of radar and related technologies. Within this environment, engineers worked under intense pressure to deliver systems that could function reliably in combat conditions. Getting's role aligned with system-level integration rather than component design. He contributed to translating theoretical navigation concepts into procedures that could be used by operators with limited training. As work on long-range radio navigation progressed, Getting became involved in the development of what would become the LORAN system. The core principle relied on measuring the difference in arrival time between synchronized radio signals transmitted from fixed stations. Getting worked on ensuring that this principle could be implemented consistently, accounting for timing precision, signal propagation delays, and operational constraints encountered in the field. A key challenge in early LORAN development was synchronization. Small timing errors translated directly into large positional errors over long distances. Getting's work addressed how transmitters could remain synchronized and how receivers could interpret time differences reliably under varying conditions. These efforts were essential to making the system usable beyond controlled laboratory environments. By this stage of the war, Getting was no longer working solely as a researcher. He was operating as a systems engineer, bridging the gap between theory, hardware limitations, and operational use. His contributions focused on ensuring that navigation outputs were predictable, repeatable, and trustworthy when visibility was poor or non-existent. The core problem Ivan A. Getting worked on during World War II was not navigation in theory, but navigation under operational constraints. Ships and aircraft needed a way to determine their position over long distances without relying on visibility, celestial references, or manual estimation. Existing radio navigation methods were limited in range or accuracy. The challenge was to design a system that could operate continuously across oceans and under combat conditions. The LORAN system addressed this problem by using time difference measurement. Fixed radio transmitters broadcast synchronized pulses. A receiver measured the difference in arrival time between signals from two stations. This time difference corresponded to a hyperbolic line of position. By combining measurements from multiple transmitter pairs, operators could determine their location with useful accuracy over long distances. The principle itself was not entirely new. What made LORAN operational was the ability to apply it consistently at scale. This required precise synchronization between transmitters, separated by hundreds of miles, stable timing references, and receiver equipment capable of resolving very small time differences. Errors measured in microseconds could translate into navigational errors measured in miles. The system's usefulness depended on controlling these errors within predictable limits. Ivan Getting's work focused on turning this concept into a reliable system. He worked on issues related to signal timing, propagation delay, and interpretation under real-world conditions. Radio signals do not travel uniformly. They are affected by terrain, atmospheric conditions, and interference. Getting contributed to methods that accounted for these factors so that timing measurements could remain meaningful in operational environments. Another challenge was usability. LORAN was intended for widespread military use, not for specialists in radio physics. The system had to produce outputs that operators could interpret quickly and consistently. This required simplifying procedures, standardizing measurements, and defining operating limits. Getting's systems-level approach helped ensure that LORAN functioned as a navigational tool rather than a laboratory experiment. As the system matured, LORAN demonstrated advantages over existing navigation methods. It functioned day and night, in poor weather, and over distances where visual or celestial navigation failed. It allowed ships and aircraft to maintain formation, follow planned routes, and reach targets with greater accuracy. These capabilities were especially important in the Atlantic, where long-range navigation errors could accumulate rapidly. LORAN did not eliminate navigational uncertainty, but it reduced it to a manageable level. Engineers accepted that absolute precision was impossible. The goal was consistency and predictability. By defining timing tolerances and system limits, LORAN provided position estimates that commanders could trust within known margins of error. This reliability mattered more than theoretical accuracy. The system was deployed incrementally, refined through field experience, and adapted to different operational needs. By the later stages of the war, LORAN had become an integral part of Allied navigation infrastructure. Its success was not the result of a single invention, but of engineering decisions that prioritized synchronization, stability, and repeatable performance under pressure. Should a navigation system be judged by theoretical accuracy or by how consistently it performs under real operational conditions? As World War II progressed, LORAN moved from experimental deployment to operational infrastructure. Its value became most evident in environments where traditional navigation failed. In the North Atlantic, convoys travelled vast distances under poor weather conditions, limited visibility, and constant threat from submarines. Small navigational errors accumulated over time, increasing exposure to enemy patrols and delaying coordinated operations. LORAN reduced these uncertainties by providing consistent position estimates over long ranges. Naval operations benefited directly from this reliability. Convoy routes could be followed with greater precision, reducing dispersion and improving coordination between escort vessels. Course corrections could be made based on measurable data rather than estimation. This did not eliminate risk, but it reduced the navigational drift that previously compounded operational vulnerability. The system allowed commanders to plan movements with clearer expectations of where forces would actually be located. Air operations also relied on LORAN. Long-range patrol aircraft and bombers operated beyond the reach of visual landmarks and often under cloud cover. Celestial navigation required clear skies and time-consuming calculations. LORAN provided a faster alternative that functioned regardless of weather or daylight. Aircraft could maintain planned routes and approach target areas with improved positional awareness, even when visual confirmation was unavailable. Amphibious and large-scale coordinated operations depended on timing and positioning across multiple forces. LORAN contributed to this coordination by allowing ships and aircraft to synchronize movement over wide areas. When operations involved staggered arrivals or converging routes, predictable navigation reduced delays and misalignment. These effects were incremental rather than dramatic, but they accumulated across repeated operations. The success of LORAN was not based on achieving perfect accuracy. It was based on known error bounds. Commanders and operators understood the system's limitations and planned accordingly. This predictability allowed LORAN to be integrated into decision-making rather than treated as an experimental aid. Reliability within defined limits proved more valuable than higher accuracy that varied unpredictably. After the war, the principles behind LORAN did not disappear. The system continued to evolve in peacetime navigation and influenced later developments in radio-based positioning. Ivan A. Getting carried this systems-oriented approach forward in his post-war career. He became involved in early discussions and research that shaped satellite navigation concepts, contributing to the intellectual groundwork that later led to the global positioning system. The transition from LORAN to GPS represented a shift in scale rather than in principle. Both systems relied on time measurement, signal synchronization, and controlled error. Margins. The environment changed from ground-based transmitters to satellites, but the core engineering problem remained the same, turning signal timing into reliable position information. Getting's wartime experience with LORAN informed this transition. Ivan Getting's contributions illustrate how World War II was shaped not only by weapons and platforms, but by systems that controlled movement and coordination. LORAN did not win battles on its own. It reduced uncertainty in an environment where uncertainty carried strategic cost. By enabling forces to know where they were with reasonable confidence, it influenced how operations were planned and executed. In evaluating wartime success, should greater weight be given to weapons that destroy or to systems that reduce uncertainty before combat begins?